Okay, introduction to electricidad. Static electricity. Never trust an atom. They make up everything. So, atoms make up everything around us. And as you've probably heard this rumor too, every atom has a small, dense core surrounded by a negatively charged electron cloud. I should say cloud, not charged. One thing you may not know is just how small is the nucleus and just how dense is the nucleus. Does anyone know without looking it up? How small is the nucleus? Super small, is correct. How small? Anyone ever heard if the nucleus is the size of a tuna can, how big is the rest of the atom? You think it's as big as me? As big as the Earth? As big as ASU? What do you think? Put it down in the Google form. Question today: if a nucleus is the size of a can of tuna, how big is the electron cloud for an atom? What do you think? Take a guess. What? Stop. Don't look it up, by the way. My smooth brain. Aw. Womp womp. Bigger. Yes, bigger is correct. Take a guess. Come on. If you just said bigger, take a stab. Okay, so I've got someone saying that if the size of the nucleus is a can of tuna, the size of the electron cloud is a needle point. No, it's bigger. I'll give you a hint. It is bigger. How much bigger? Again, the question is, oh, hey, people online, can you hear better now? The question A in the Google form is, if the nucleus of an atom is the size of a can of tuna, how big is the electron cloud surrounding it? Give a stab. Okay, and the correct answer. I'll give. Come on. Just take a guess. Huh? It is absolutely, I'm looking for a rough order of magnitude because there are lots of different atoms with lots of different nuclei, and it's not the same at all. Abigail's got it. It's the size of a football field, roughly. Can of tuna to a football stadium in particular, not just the football field, the stadium.
Yeah, that's it.
You're looking at a factor of 1 part in 100,000. The rest of the atom, the electron cloud, is about 100,000 times bigger than the atom itself. So proton size, nucleus size is on the order of magnitude the same size as protons and neutrons. What sticks in my head is a femtometer, 10 to the minus 15 meters is the size of a proton, a neutron, a nucleus, that order of magnitude. What sticks in my head for the size of an atom is an angstrom. Actually, half an angstrom is the Bohr radius. Who's heard of the Bohr radius before? I'm sorry, am I boring you? The Bohr radius is the size of the hydrogen atom, and that's something like 0.5 times 10 to the minus 10 meters. That sticks in my head anyway, half an angstrom. Okay, I'm interested to see. Yeah, about half you guessed small, half you guessed bigger. 5 cans of tuna. Oh no, much bigger. How about size? How about mass? So that's physical size. That's length. What about mass? Don't look at this. How heavy is the electron cloud versus the nucleus? No. I'll just tell you. Fine. Okay. Think about it. Take a guess inside your head. The answer is it's again at that about a factor of 1 to 100,000. Something like that. An individual electron, mass 10 to minus 30 kilos. An individual proton or neutron is something like 2,000 times, 1,800 times as massive as each electron. However, you may have heard that protons and neutrons like each other. They belong together inside that nucleus. So something like copper. What's copper? 32, element 32, right? 32, 20 something? whatever. 32 protons, about as many neutrons, or whatever the standard isotope of copper is. You've got something like a factor of 100 times something like a factor of 2,000 on the order of magnitude of 100,000 times more massive nucleus than individual electrons. So, orders of magnitude. I'm not going to test you on numbers, by the way. I do not care about you memorizing numbers, but I would very much like you to have a gut feeling about this. Electron clouds take up the vast majority of your volume, and they are ghosts, man. They're wispy clouds. 1/100,000th of the mass of the nucleus and 100,000 times the size. What does that mean? 10 billion times denser. The nucleus is 10 billion times denser than 10 orders of magnitude denser. It's crazy. No, more, whatever. Screw it. Okay, so size, good, great. Mass, good, great. Charge-wise, you know this, surely. The magnitude of charge of a proton is equal to the magnitude of charge of an electron. So when it comes to physical dimensions, size, mass, the nucleus is huge and dense. Huge mass, tiny size, very dense. And the electrons are basically nothing, but they interact electrically, they interact equally strongly. So what we're going to talk about is if you have electrical forces that act on the protons and act on the electrons, those electrons are they're going to skippity on out of there because they're so lightweight. The relative strength of electrical forces is huge compared to their size. The nucleus, the rest of the atom, is big, dumb, fat, and staying where it's put at because it's experiencing the same amount of force and its mass is so much bigger. When we are talking about static electricity, when we are talking about current electricity, it's very largely the story of the electrons. Why? There's nothing fundamental about that. It all goes back to these facts. Electrons are just so light and easy to move. That's why the electrons are so important. Please note, by the way, atoms are J random atom that you meet is going to be electrically neutral. What does neutral mean? It means they got a lot of guns and they got high mountains. Sorry, that's Switzerland. Sorry. All atoms are neutral. That means they have equal number of protons and electrons. Yeah. Good. Neutral, no net charge, equal protons and neutrons. Protons and electrons, yeah? Everyone knows all that. Yeah. Maybe not the exact numbers, but all that's review. Great. No, which device has it got on? Second slide of facts here. Electrons, I should say atoms, can be monogamous or they can be swingers. We call monogamous atoms, we call them insulators, we call swingers conductors. That is to say, atoms can hold on tightly to their electrons, or they can be very promiscuous with their electrons and let them flow where they may. A material where the electrons are strongly bound is an insulator. A material where the electrons are weakly bound or not bound at all in the conducting shell is called a conductor. I'll write this down, note this, think about this. Outer shell electrons in a conductor are not anchored to particular nuclei. We call this you will see references to this from time to time. We call this the electron sea. You got a piece of copper or whatever. The outer shell electrons can float freely from atom to atom. Very easy for them to move from one place. Very, very easy to move from one place to the other. I shouldn't say absolutely zero energy cost, but absolutely negligible, small energy cost. Air is a great example of an insulator. An insulator like air is very difficult to get an electron to go from here to there, from this atom to the next atom of air. What happens when we have electricity pass through air? That's called lightning or a spark. That's relatively hard to get to happen. You have to put a lot of energy into that. Electricity flows very freely through a conductor and relatively difficult to get it to flow at all through an insulator. Please note, Conducting, insulating is a continuum. It is a spectrum. It is not either you are a conductor or you are an insulator. There's more to the world than just conductors and insulators. There are good conductors, there are bad conductors. There are good insulators and there are bad insulators. And there are things that are neither. It is beyond the scope of a class to tell you about superconductors, but I just want to admit that there is something, there's an advanced material that is currently class materials that are under study now. It just actually makes its way into everyday electronics, consumer electronics. There would be an absolute revolution. There are materials that have no electrical resistance whatsoever, 0 ohm resistance. It's called superconductor. That is not a classical physics phenomenon. I cannot deduce that that exists from our picture of resistance and resistivity. But actual resistivity can be, in fact, 0. It's quantum mechanical phenomenon. There's also materials, this is also sadly beyond the scope of the course, but I do want to mention that it exists because this is, every one of you has one of these either in your pocket or your lap represents it. Semiconductors are things that are halfway between conductors and insulators, and very importantly, can be changed from conductor to insulator electronically. What makes your CPUs, what makes your processors, what makes your tablets electronics circuits more than just an on-off light, everything more sophisticated than the power light for your electronics. So you have a semiconductor, something where the flow of electricity can be itself electrically manipulated. There's far more to your computers, your tablets, your phones than just resistive circuits. Unfortunately, that's outside the scope of what we could do in this class. But I want you to at least know that it is a thing. Oh, what did I just say? Google, not Google, yeah, Google Form B. What is a neutral object? And please don't type the whole darn thing out. ABC. Bigger. A neutral object is not bigger. Yeah, it's Google Form B. Thanks. Okay, the correct answer is C. I defined it as having no net charge. No charges of either sign, that's only neutrons. Neutrons are the only object that has nothing with no charge. Everything's made of atoms in the world around you. By the way, nothing is made of just neutrons in the world around you. Nothing that you are familiar with is pure. Can have isolated neutrons, neutron stars, laboratory experiments, but that's not what you're made of. Everything in the world around you has charge in it. It's just, are they balanced or not? If they're balanced, that's electrically neutral. What's B? If you put B to this, what's an insulator? An insulator is monogamous. They're pair bonded. They don't share. Their electrons are stuck on the proton, the nuclei that it starts with, and they don't flow around nicely. That's an insulator. Nothing to do. You could have an insulating charged object. You could have an insulating neutral object. You have a charged conductor. You could have a neutral conductor. Completely different things. Don't get them confused. Turn to your neighbor real fast and discuss. What is the difference between neutral and insulator? Thumbs up. Questions? Is good? Next question. Hey, what's a coulomb again? Coulomb is the unit of charge corresponding to, and I will remind you of this fact, 6.25 billion charges. 1 coulomb, 6.25. I think I said 6.24 earlier. 6.25 is closer. I rounded wrong. You will need that to solve this problem. Put your answer in C. Good, Rami. Good, Sabrina. You two win the prize. Christian, good job. All right. Hmm, 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 hmm. I went into this deeper with the 3 o'clock class. I don't know. I don't know, man. Should I go deeper in here? Yeah, there's a fair number of mistakes. All righty. No, one more minute for as many people as possible to finish it. Or let me try a different way of explaining it. If you know clicky yet. If you got 1.25, 10 to the 11, great, you're done. If you didn't, please consider the following. I'm going to try a new way of explaining it from what I said before. What happens if I multiply something by 1? Does it change? I am going to tell you that 6.25 times 10 to the 18 is the number of charges in 1 coulomb. In other words, 6.25 10 to the 18 charges divided by 1 coulomb is 1. Charges per each coulomb. If I multiply some number of coulombs by this number, the units change. Coulombs divided by coulombs cancel, and I'm left with charges. But I haven't changed the amount. Suppose I have 1 coulomb, and I multiply this 1 coulomb times 6.25 10 to the 18 charges per coulomb. Coulombs per coulombs cancel. I'm left with 6.25 10 to the 18 charges. Right? I mean, that should make sense. What happens if I have 3 coulombs? If I have 3 coulombs, and each coulomb consists of 6.25 billion charges, coulombs cancels coulombs, multiply 3 times 6, whatever that is, and I get that number of charges. Have I changed the amount? I had 3 coulombs, now I have 1.8 times blah, 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 blah. No, it's still the same thing. It's just instead of expressing in terms of 3 coulombs, I'm expressing in terms of blah, 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 number of charges. Blah, 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 blah stands for whatever you get when you plug in your calculator. I don't have 1. I don't have 3. I have 20 nano. What's a nano, by the way? You have to know nanos. You know picos to gigas in this class. If I have 20 times 10 to the minus 9 coulombs, and each coulomb consists of blah, 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 charges per coulomb. Coulombs over coulombs cancel, and I can simply multiply together. 20 times 6.25 times 10 to the minus 9 times 10 to the positive 18 works out to be 1.3-ish 10 to the 11 charges. So unit conversions we can think of as multiplying by 1, not changing the amount, but changing how we're expressing. Oh, that's just thought. So the charge of 20 nanocoulombs is composed of how many electrons? This many electrons. It is not negative electrons. By the way, actually, a fair number of people in the 3 o'clock class told me that they have negative number of electrons. Be careful, don't double count your negative signs. If you are very firm on believing, if you're very confused about this, let me make the following proposition to you. I'm going to give you my household bills. I'm giving you a debt. I will give you a positive number of my bills, okay? You're getting a positive number of them. Here, take my water bill. Here, take my electric bill. You are getting a positive number of them. That's good for your finances, right? Right? You get a positive number of negative things, you're going down. I told you that the electrical charge is negative amount of charge. How do I get a negative amount of charge? I have to give you a positive number of electrons. Don't double count. It's not negative electrons. Does that feel okay? Watch out for that, by the way. I can neither confirm nor deny that this is one of the questions on the next midterm. By which I mean, I think it's one of the questions of the next midterm, but I don't remember if I've said it yet. Think about this. Positive number of electrons is negative charge. Hey, the other big goof that I want you to look out for, watch out for. What does x to the negative 1 mean? 1 divided by x to the 1? 10 to the negative power. What can we say is always true about 10 to the negative something power? 1 over 10 to that power. Always less than 1. If you told me 10 to the negative something electrons, you just told me that you could break an electron into some number of pieces. We have never, ever observed a fractional electron. You will never, ever have 10 to the minus something number of charges. You could have 10 to the negative 9 coulombs, but if you've converted to charges, electrons, protons, you will never have a negative exponent, because that means a less than 1 amount of protons and neutrons. And almost nobody told me the 10 to the negative 11. The 3 o'clock class, it was like, I don't know, 10% of the class. Good. Okay. Let's move on. I just reminded you of this. Fundamental charges are measured not by the unit, but by the coulomb. And 1 coulomb, 6 1/4, 10 to the 18 fundamentals. I will also point out and remind you, if it takes 6 charges to make a coulomb, each charge is 1/6 billionth of a coulomb. This number is worth writing down. That is to say, put this in your notes or on an equation sheet or somewhere in your binder where you can find it quickly, because you're going to be calculating in terms of single charges a fair amount this module. Put this somewhere you can find it quickly. 1 divided by 6.25 10 to the 18 is the charge on a fundamental particle, a proton or an electron. And it has value 1.60 10 to the negative 19 coulombs. It's just the reciprocal of this number, but it pops up enough to be useful. Wait, should E be a positive or a negative number? How did I define gravitational field last semester? G is Positive or negative 9.8? No? I defined G is 9.8. Acceleration of a falling object is then negative G. G downward. E is the magnitude of the charge. The charge on an electron is negative E. Okay, watch out for this. This quantity, E, is not electron. Electrons are negative. The charge on an electron is a negative number. This is his magnitude. Making sense? So TLDR, wake up. This is a positive number. If you're talking about an electron's charge, the charge on an electron is negative that number. I mentioned that charge is symbolized Q before. Now there's a distinction I want to make. We express charge as Q equals some number of coulombs, but lowercase or capital Q, both are actually used. It is common to express both. Not every textbook uses this. Not every online resource YouTube video uses this. I encourage you to. I will most of the time do this myself. Capital Q refers to causes, lowercase q refers to effects. That is to say, I will call capital Q source charges, lowercase q test charges. What's the difference? Well, they're all the same thing. They're all charges. But whatever I'm referring to as lowercase q is the object under study. For instance, suppose I've got 4 charges, A, B, C, and D, and I want to know how A, B, and C push on D. I would symbolize these QA, QB, QC, and little q. Little q is D. Little q is the 4th one. Little q is whatever one I care about being pushed on. If I were asking how do B, C, and D push on A, I would refer to them as little q, big QA, big QB, big QC, big QD. So any given charge, is it a capital or is it a lowercase? Well, is it the thing that I'm asking about the force on? If it's the thing that I'm asking about, how is this being pushed or pulled, then it's a lowercase q. Otherwise, it's a capital. See that distinction there? It's just notation, but it can be useful. Help you catch errors. See this more later. It's also permissible to just write Q1, Q2, Q3, whatever. Who cares? You don't have to. I will occasionally slip up and write Q1 times Q2 instead of Q times big Q. We'll get there. I do want to emphasize, by the way, don't confuse Q and C. Sometimes, from time to time, I see students write, m equals 5 when they mean that meters equals 5. That's silly. M equals 5 means mass is 5. Q is the algebraic symbol we use. C is its unit. Just like x equals 5m means the position x is the algebraic symbol that you use in calculations, is at 5 what unit? 5 meters. The unit is the meter, m. The symbol is the x. Yeah? Coulombs. Coulombs are the unit, and Q is the algebraic letter that we use to symbolize it. Okay. Everything we've done up till now has either been notational or review from some point or other. Now let's talk about something new. Did you know that you can attract a neutral object with a charge? What? What's the base rule of electricity? Opposites attract, like charges repel, right? However, since you also know that neutral objects have lots of pluses and minuses in them, they're made up of atoms, atoms have parts, there's something cool that goes on. If I bring an external charge near a neutral object, charges can rearrange inside that object. Example. Suppose I have a balloon here that I rubbed on my hair, it's got a positive charge, and I bring it near an aluminum can. I've got a positive charge. What's that going to do to the positives in this can? Push them which way? What's it going to do with the negatives in this can? What will happen is that you will end up with some minuses on one side and some pluses on the opposite side. Couple of quick pro tips for understanding this. You'll do this more in lab, by the way. Couple of pro tips: charges are always on the outside, as far away or as near as they can get. Always on the outside, always as far and as near as they can get. You will end up with a plus side and a minus side on the can. Now, electricity, just like magnetism, is distance dependent. When you hold magnets here versus if you hold them here, is there a difference in the force? When you bring magnets closer together, do you feel them pull each other harder? You betcha. I'll tell you the form of the formula for electricity momentarily, or in a few minutes. The closer the charges are, absolutely the stronger they pull. So what's going to happen? This plus is going to attract these minuses. This plus is going to repel these pluses, which is stronger. The attraction. Why is the attraction stronger? Because it's closer. Yeah? So if I bring in a positive charge near a neutral object, it will attract that neutral object. You could rub a balloon on your hair and take an empty soda can and attract it across the table. Fun party trick. If you go to the kind of parties that I do, anyway. Which is nothing now that I have a 1-year-old. Anyway, point is, I would now like you in the Google form to tell a prediction of what happens if I bring in a negative charge. Will a negative charge attract or repel? What? D? Here. I'm going to bring in a negative charge instead of a positive charge. Is that going to attract or is that going to repel? All right, let's reason through it. I bring in a negative charge. There are pluses and there are minuses inside my neutral object. What's going to happen to the plus charges? Pull towards. What's going to happen to the minus charges? Which is closer? The attractive force or the repulsive force? Which is going to win? Does it matter that I bring in an external plus or an external minus? In the Google form, does it matter if I bring in an external plus or a minus? Question E. Correct answer is it doesn't. Regardless of what external polarizing charge you bring in, you're going to attract the attractive charge. The attracted charge is going to be the one that attracts. So he's closer, so he's stronger, so the total force is going to be attractive. Doesn't matter if you bring in positive or a negative external, the result is a neutral object will polarize and be attracted. Now, there are a couple of science things to know about this other than just neutral objects can be attracted by charged objects. I want you to think about what is happening within the charged object. The opposites near are pulled near, the lights are pushed far away, but not all of the charges move. In practice, you might end up with 1 billion charges move. 1 billion charges, is that a lot of charges? It's even more than my bank account, sure. How many atoms are there in a soda can? Do you think there's more or less than a billion atoms in a soda can? What do you guys think? Give me a thumbs up if you think there's more than a billion atoms, or a thumbs down if there's less than a billion. Let me remind you that Avogadro's number, 6 times 10 to the 23rd power, is the number of grams for 1 mole, the number of atoms in 1 mole of the substance, and the atomic number of aluminum is what, like 50 something? What am I trying to say? 56 grams of aluminum is 6 billion thousand charges, right? Right? 10 to the 23rd is a really big number. You got an aluminum can, a few grams of aluminum is billions of charges. So yes, if I put a billion free electrons on an aluminum can, that's a lot of electrons. But compared to the total number, it's not. When we have electrostatic experiments, you're going to be transferring something like nanocoulombs of charge on the order of billions of electrons are going to go from this object to that object in your static electricity experiments in the lab. That's totally reasonable. But I want you to know that is nothing like, nowhere even close to remotely distantly related to all of the charges of the object. You can always transfer more. There are billions of times more unaffected ones than Thing 2 to know. Charge, this is subtle, pay attention. Charge stops rearranging once external forces balance the internal forces. What? Consider an internal plus charge here. Okay, so I've got an external charge, polarizes, negative polarizes this neutral object out. Pluses on the left and minuses on the right. Consider an internal charge here. Is it attracted or repelled by the external charge? Which direction is it pulled by that guy? Left. Yeah? It is attracted leftward towards this guy. Which direction is it attracted or repelled by these charges, the internal charges? Positive, left or right? Okay, take a look up here. Take a look up here. Whatever you do with positive or negative there, this is going to exert a force in the opposite direction that these would exert on a free charge on the inside. Does that make sense? If this is negative, the force on a free charge, free positive, would be leftward. And these would exert a rightward force, right? No matter what you do. If this is positive, then you'd end up with a negative here and a positive here. And the forces would still be opposite. The force of the external on an internal and the polarized charge on the internal. We'll point in opposite directions. I claim that polarization will continue until the external attraction balances the internal attraction on a free charge on the inside. Beatings will continue until the morale improves. Polarization will continue until the polarization charge balances the force from the polarized charge. These guys better balance that. So, TLDR, what's the big takeaway here? Charge continues to rearrange until the total force inside the conductor is 0. Write that down. Total force on a free charge in the conductor is 0. Total force on a free charge inside a conductor is 0. On a free charge in a conductor is 0. Put it in your notes, not in the Google form. How do I know total force on a free charge inside a conductor is zero? Because if there were a net force, charges would continue to flow. I should say in static equilibrium. You can have charges continue to flow if you continue to pump them. If you've got a battery attached to a resistor, charges will not, reach an equilibrium state. They will continue to be pushed. In static electricity, inside a conductor, there's no net force. Again, I'd like you to think through this. This is something you can deduce from logic. Total force on a free charge inside a conductor has to be balanced to zero. Otherwise, if there's still a force, you'd still get more movement. And you wouldn't be in equilibrium. Then you get more charge flying out to the ends. Stronger force, stronger force, stronger force, stronger force, eventually you'd unbalance. Turn to your neighbor and express this idea. Total force on a free charge inside a conductor is zero. Why? Because if you did still have a force, then you get more charge piling up until you have a balance. Yeah? Turn to your neighbor, discuss real fast. So we're talking about different things in the first example and the second example. The first example, I was saying the full force on the total polarized object, total neutral object, total force is attractive because the attracted parts are closer. Now I'm saying, all right, consider a free bit, another electron, another proton inside the material. A free charge inside the material. Sucker there. Doesn't matter if it's a proton or an electron, I drew a plus, whatever. This is going to be, has to be equally pulled left, pushed right by the internal and the external. If there were still more force from here, if this guy is still pulled left, then he will add these pluses. There'll be more plus in there for another guy to feel. How? You know what? There's a really good analogy we made here with politics. Not perfect, but like anytime you got a good idea about what will make the world better, what happens to the other side? They get political traction by opposing that idea. Any good idea that one side comes up with, the other side can make mileage off of opposing it. And what happens? At the end of the day, you have a balance so that a third of the voters of the country are going to say, nope, both sides are equal. And that is as far as I'm going to push that analogy, ere I violate ABOR regulations. The rearrangement of charges within a conductor happens on the order of nanoseconds of time. Nanoseconds. In our labs, you are never going to observe the charges continuing to rearrange. That does not mean that there is no circumstance in which you do have charges not reach equilibrium in time. For instance, if you have a really fast alternating current, for instance, if you have a ham radio antenna, the antenna depends on this rearranging not coming to a balance. That's the unscoped class. For our purposes, when we're talking about static electricity, the rearranging is effectively too fast to notice these things. And once we reach the balance, there's no further force on the electricity in the charges inside the conductor. Again, why is there no further force? Because if there were still a force, more rearranging would happen. Note, as I said before, rearrangement happens, pushes. Wait, did I say this before? Did I already say they go to the outside? Rearranging happens to be pushes as far and as close as possible. That means, pro tip number 2 that I may or may not have said, write this down. Free charges are always found on the outside of the conductor. You never have free charges inside the conductor. They always end up on the outside, as close and as far away as they can get. Please note, please note, please note, please note. I just described how a neutral object can end up with positive and negative sides. We call it a polarized object that can attract or be attracted by an external charge. The total charge on a polarized object, we don't turn a neutral object into a charged object. A plus charge can attract a zero total charge object. We are not giving the opposite charge to our neutral object. The amount of plus and the amount of minus in my example that I did over here, there's the same total amount of plus and the same total amount of minus. These balance. It's a non-charged object there. It's a neutral object, neutral but polarized. Okay. Net charge on a polarized object is still zero. You're only attracted because there's a position dependence on those, okay? Now, I've been talking about conductors left, right, and center for a good reason. Polarization effects on conductors can be big. There's no limit. The only limit to how far the charges can be shoved around is to the furthest left and right sides of the object. Insulators can do this as well. Insulators can polarize as well. They don't work by free charges moving all the way from one side of the object to the other side of the object. It is the individual atoms or molecules stretching, realigning, rotating within the object. Look, if I've got water, say water is a good polarizable neutral object. Pure water is a good insulator. I don't know if you've ever heard that before. Deionized water, great insulator. If I bring a positive charge, let me bring a positive charge near a bottle of water, what's going to happen? The various water molecules are going to orient so that their attracted side, in my example here, their negative side is on the left and their positive side's on the right. What do you notice about the minuses and the pluses inside the bottle of water? Draw as many as you want. Keep drawing, keep drawing. What do you notice? Any given plus is next to a minus. Any given minus is next to a plus. Well, there we go. Every given plus is next to a minus, except on the outer surface. Look at that. Look. What is happening on the entire left side of the object? There's a whole bunch of negativity. What is happening on the entire right side of the object? There's a whole bunch of positivity. These are not free positives and negatives. You can't take them off and use them for stuff, right? They're part of molecules. But on the left side of this object, there's a whole surface of negativity. On the right side of this object, there's a whole surface of positivity. That has an electrical effect. you still have a polarized object. Even though those pluses and those minuses are attached to stuff, that doesn't negate the fact that they are still spread from, moved from being, they're still moved so that there's a negative and a positive side of your neutral object. You've still got a polarized object. What happens if you just got a bare hydrogen? Hydrogen is completely nonpolar, right? Right? There's a positive nucleus and a negative electron around it, right? Well, if I have something without polar ends, a non-polar atom, if I apply an electric field, if I bring in an external electric charge, I can still deform the electron cloud. You can have an electron cloud which is not centered on your hydrogen proton. You can still have a polarized neutral atom. There could still be a positive, there could still be an electron cloud which is shifted to the side. The bulk effect is you could still have a polarized neutral element, even if it's a nonpolar molecule normally. What's the big takeaway here? Neutral objects polarize as well, although it's often a smaller effect from conductors. Did I just say neutral objects polarize as well? I should be taken out behind that and whooped. Insulating objects can polarize as well as conducting objects. It's often a smaller effect, but it's still there. Okay, Google form. Fast as you can. Chop, chop, chop. Question F. What do you think? A, B, or C? Real fast. Let me see your answers. What did we describe in exhaustive detail? You and me both, Mr. iPad. Cool. Water, deionized water is good. But water molecules are polar, right? They've got a oxygen has the negative side of the water molecule. The hydrogen's the positive side of the water molecule. Could be what? Yeah, it still happens too fast. You can actually calculate how long that takes. That's a fun calculation, but that's also beyond the scope of our calculation abilities in here, but it's still really fast. Okay, correct answer is A, attractive. A, attractive. You polarize an object, regardless of conducting or insulating, you polarize an object, the attractive side is closer, it's gonna pull you. I will also point out here, like I have 5 other points in this lecture, say that there is active research going on here. There are materials that do not polarize according to the rules that I've given here. You can apply an electric field going this way and get a polarization that way in some metamaterials. This is something which is currently being researched at ASU, not in my lab that I did my PhD in, but in the ASU physics department. If people figure out how to make this into consumer electronics, we're talking absolute revolution, absolute technological revolution. So look out for that over the course of the next decades. Absolutely. Polarization, I am describing physics 112 level polarization, but I do want you to be aware that the logic that I said, there are, this is what I want you to know. This is what I want you to be able to reason about. But there are weird, spooky quantum mechanical tricks you could play with materials that can get them to polarize differently, can polarize at right angles If I bring in a positive charge over here, the positive ends up over here, the minus ends up over here. And this may be part of tomorrow's computer, the next generation of advanced technology. Active research. For us, we're going to pretend that the universe is simple and that you have never heard of quantum mechanics. For us, in our class here, it's always going to be attractive. I am going to recognize that it is 5:34 and present to you the Coulomb's law for force between 2-point charges. I'm going to point out that I will occasionally write it 2 different ways. Like I said before, Q, Q1, Q2, potato, potato. Here's something that you will see in notational differences. If I recall correctly, your textbook uses D. I inevitably go back to the way I was first taught, which is using R. The downstairs in this formula is the distance between the 2 charges in meters. R or D, in either case, whatever letter you use, means the distance between the 2 charges that are pushing or pulling on each other. K, constant nature, 8.99, 10 to the 9. You don't need to memorize the units, those are SI units. Q1, Q2, or little q and big Q, the magnitude of charge of each object that is exerting a force on each other. KQQ over R squared is how I'm going to be banging on this table and saying it again and again. Please, 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 please memorize fast. There are going to be 4 formulas that look just like each other, that are only different by 1 letter each. And if you confuse them for each other, you're screwed. I would really like it if you don't wait until just before the midterm to try to start distinguishing between these. These units, nah, it's just these are the SI units. You don't need to memorize the units. You need to know 8.99 times 10 to the 9 in standard units. But the structure of the formula, K times the magnitude of each charge multiplied by each other, divided by the distance between them squared, that, get into your heads fast. As soon as Wednesday, I'm going to introduce the second of the 4 formulas that are all going to look like each other. And we got more than 4 formulas to do too. It's not, that's everything. Okay. Ross Tucker, who's that nerd? Oh, that's me. Okay. I'm gonna cut it here. We will meet again on Wednesday and start with the electric field.